the end of this lesson, you'll be able to draw the full adder circuit from memory, derive every equation in it, and defend every gate, including the one question professors love to ask: why is a single OR gate enough? Let's earn it. Everything starts with a skill you already half own: binary addition. Here's the intuition. It's the same column addition you learned as a child. Right to left. Carry whenever a column overflows. The only difference? A binary column overflows at 2, not 10. That gives us 4 facts. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And the one that matters: 1 plus 1 is 1, 0. Not 10, 1, 0. A sum bit of 0 and a carry bit of 1. Here's a useful way to remember it. 1 plus 1 is 1, 0. One more fact before we move on. 1 plus 1 plus 1 is 1, 1. Sum 1. Carry 1. Keep that in mind. It decides the hardest question later in this lesson. Let's make it concrete. Add 1, 0, 1, 1 and 0, 1, 1, 0. That's 11 plus 6. The rightmost column, 1 plus 0. Just 1. The next column, 1 plus 1, 1, 0. Right 0, carry 1. The next column, that carry plus 0 plus 1. 1, 0 again. Right 0, carry 1. The last column, carry plus 1 plus 0. Right 0, carry 1. And that final carry falls out the left side. The answer? 1, 0, 0, 0, 1. 17. Correct. Now, a common misconception. Many students quietly believe 1 plus 1 equals 1. That's OR, not addition, or throws information away. Arithmetic has to keep it. And the information OR loses is precisely the carry. That fact matters. So before moving on, 2 things to hold on to. Binary addition overflows at 2, and the carry is real data, not bookkeeping. Now that we can add on paper, here comes the engineering move of the whole lesson. Think about what we just did. Every column performed the same tiny job. Bits in, sum bit out, carry past left. So we don't build a machine for whole numbers. We build one machine for one column and then copy it. Where do we start? With the easiest column, the rightmost one. It receives only 2 bits. Call them A and B, and no incoming carry. What must it produce? Remember, 1 plus 1 is 1, 0. The answer needs 2 bits, so the specification is 2 inputs, A and B, 2 simultaneous outputs, a sum bit and a carry bit. Both outputs at the same time, every time. They're not alternatives. 2 inputs means 4 possible cases. 4 cases, 2 outputs each. That's a truth table. Let's build it in our heads. This device is the half adder. What is it? The circuit that adds 2 single bits? Why does it exist? Because the rightmost column of every addition needs exactly this job done. Here's the mechanism. Compute each case as arithmetic, then reread the result as logic. Both inputs, 0. Sum, 0. Carry, 0. 0 and 1. Sum 1, carry 0. 1 and 0. Sum 1, carry 0. And the big one, 1 and 1. 1 plus 1 is 1, 0. So sum is 0, and carry is 1. Now listen to the sum outputs in order. 0, 1, 1, 0. The sum is 1 exactly when the inputs differ. There's a gate that does precisely that. XOR, exclusive OR. 1 when the inputs differ, 0 when they match. But here's the deeper way to hear it. XOR produces exactly the sum bit of 1 bit addition. XOR is addition with the carry thrown away. If you remember only one sentence from this section, make it this one. XOR is addition without the carry. And check the dangerous case. When both inputs are 1, OR would say 1, but arithmetic demands 0. So the sum is not OR. This is where many students go wrong. Now the carry outputs in order. 0, 0, 0, 1. The carry is 1 only when both inputs are 1. That's AND by definition. So here's the formal result. Sum equals A XOR B. Carry equals A and B. Put differently, the carry and sum together read as a 2-bit number are the value of A plus B. And the hardware is just one XOR gate and one AND gate, sharing the same 2 inputs. That's the entire device, the anchor. Sum is XOR, Carry is and. A common exam mistake is swapping those two equations under time pressure. Recover it logically. Carry means both bits were 1 and both is and. And when the words half adder appear on an exam, your brain should instantly jump to sum equals A, XOR B, carry equals A and B, plus the 4-row table. Free marks in step 1 of every larger adder problem. One more thing, because it generalizes far beyond today. Notice the workflow we just used. When any exam asks you to design a small combinational circuit, immediately think specification, then truth table, then equations, then gates. That pipeline designs every combinational circuit in your degree. So the key idea of this section: the half adder is XOR for sum and for carry derived from arithmetic, never memorized. Now that we understand the half adder, let's watch it fail on purpose. Try adding two 2-bit numbers, 1, 1 plus 0, 1, using only half adders. The first column is fine, 1 plus 1. The half adder outputs sum 0 and sends a carry to the left. But now the second column receives 3 bits. A is 1, B is 0, and there's that incoming carry. The half adder has only 2 inputs. There is no door for the carry to enter. We're stuck. Pause on that. The failure itself is the next specification. Every column except the first receives 3 bits. The half adder does half the job, and that is exactly why it's called a half adder. Remember it this way: half adder, half the job. No door for the incoming carry. A common misconception: that half refers to having 2 inputs, or half the gates. No, half the function. It cannot accept a carry in. And when an exam asks why half adders alone can't build a multi-bit adder, your answer should jump out instantly. No carry in port, and middle columns receive 3 bits. 2 sentences, full marks. The section in 1 line. Real columns need 3 inputs, and that necessity defines the full adder. With that failure understood, we can finally meet the device this lesson is really about: the full adder. What is it? A circuit that adds 3 single bits, A, B, and the carry in. Why does it exist? Because 3 bits is what a real addition column receives. Its outputs, as always, a sum bit and a carry out. 3 inputs means 8 cases, 2 times 2 times 2. If you ever write this table, order the rows by counting from 0 to 7 in binary, because a skipped or shuffled row is the most common table error in exams. But here's the beautiful part. You never need to memorize those 8 rows. You could generate any of them. The trick: the carryout and sum read together as a 2-bit number are simply the count of ones at the inputs. Count the ones, write the count in binary. That's it. Hear it in action. No ones at the imports? The count is 0, 0, 0, both outputs, 0. Exactly 1 input high, whichever one it is. Count is 1, 0, 1, sum 1. Carry out 0. That single sentence covers 3 rows at once. Exactly 2 inputs high, count is 2, 1, 0, sum 0, carry out 1. 3 more rows done. And all 3 inputs high? Count is 3, 1, 1, sum 1, carry out 1. 8 rows, 1 roll, the anchor. And it sounds almost too simple. Carry out and sum are just the count of ones written in binary. 2 deeper patterns are hiding in there, and they're worth pulling out. First, the sum is 1 exactly when the number of ones is odd. That's XOR's signature addition without carries, applied bit by bit. Engineers call it parity. Second, the carryout is 1 exactly when 2 or more inputs are 1. The carryout is a majority vote. Let's protect your memory with a quick checkpoint. 3 facts so far about the full adder. The outputs are the count of ones in binary. The sum detects odd counts. That's parity. That's XOR. And the carry fires on 2 or more. That's majority. Now, the formal law. In words first. The 2 outputs together encode the arithmetic total of the 3 inputs. Mathematically, 2 times carryout plus sum equals A plus B plus carry in. 1 identity, and it regenerates the entire table. So when you blank on a row during an exam, and it happens, your brain should instantly jump to count the ones, write the count in binary. All 3 inputs, 1, count as 3. Binary, 1, 1. Carry out 1, sum 1. In that case, 1, 1, 1 is the most failed question on this topic. This is where many students get confused. The misconception: believing that a 3-input XOR outputs 1 only when exactly one input is 1. Wrong. XOR detects odd counts. 1 XOR 1 XOR 1 is 1, not 0. One more property worth marks. A, B, and carry-in are completely symmetric. The outputs depend only on the count of ones, so swap any two inputs and nothing changes. The carry-in is not a special kind of input. It's just a third bit of equal weight. Keep that in mind. It pays off twice before the end. The section boils down to this. The full adder outputs the binary count of its input ones. Sum is parity. Carry is majority. With the behavior fully understood, we can compress it into algebra. Two roots and exams can demand either one. The fast route comes straight from the patterns. The sum is parity, so sum equals AX or B or carry-in. The carry is majority. It fires when some pair of inputs is high. So carry out equals A and B, or A and carry-in, or B and carry-in. Hear what that says. Each term detects one possible pair of ones, and the OR asks, is some pair present? The rigorous route earns the same answer from the table. Collect the 4 cases where the carryout is 1. Write one in term per case, and OR them together. Engineers call that a sum of products. The 4 terms where not means the inverted bit, not A and B, and carry-in. A and not B, and carry-in. A and B, and not carry-in. And finally, A and B and carry-in. Now simplify in 2 groupings. The last 2 terms both contain A and B, one with carry-in, one without. Together, they cover both possibilities. So they collapse to simply A and B. The first 2 terms both contain carry-in, and what remains, B without A or A without B, is exactly A, X, or B. So everything collapses to carry out equals A and B, or carry in and A, X, or B. In plain words, either the 2 main bits carried on their own, or the incoming carry met a difference between them. 2 valid forms of the same truth. Exams love asking you to convert between them, and the classic mistake is botching exactly that factoring step. You've now heard it done correctly. Always check your result with the law. Take the case 101. The arithmetic total is 2. The equations say sum is 1, XOR 0XOR 1, 0. Carry out 1. 2 times 1 plus 0, 2. Consistent. That 30-second checksum has saved many exam grades. Now here's the moment this lesson has been building toward. Consider that final form again. Carry out equals A and B, or carry in and AX OR B. A, X, or B. A and B. Where have you heard those 2 expressions before? They are exactly the 2 outputs of a half adder running on A and B. The circuit we came here to build is already sitting inside the algebra. The takeaway. Sum equals A, XOR B, or carry in. Carry out equals A and B, or carry in and A, XOR B. And that second form is a construction blueprint. Everything we've done so far leads to the construction in the title. A full adder made from 2 half adders and 1 OR gate. Let's read it straight off the equation. Step 1. The first half adder takes A and B. It produces 2 signals, a partial sum AX or B, and a first carry A and B. Step 2. The second half adder takes that partial sum, together with the carry-in. Its sum output is the partial sum XOR carry-in, which is A XOR B XOR carry-in. And XOR is associative, so the grouping doesn't matter. That is exactly the full adder sum. Its carry output, call it the second carry, is the partial sum and carry-in. Step 3. The carryout is simply first carry OR second carry. Expand it. A and B, or AX or B and carry in. That matches our equation perfectly. 1 OR gate. Done. The intuition behind the whole structure. Add the 2 main bits first. Then add the incoming carry to that partial sum. If either stage overflowed, the column overflowed. But wait, carries are numbers. Why is a plain OR gate enough to combine them? If both stages carried at the same time, wouldn't OR lose 1? Here is the proof, and it is the classic exam question on this topic. The claim. The 2 carries can never be 1 at the same time. Follow the chain. Suppose the first carry fires. That means A and B are both 1. But then the partial sum A, X, or B is 0. And the second carry is that partial sum and the carry in 0 and anything 0. Done. If the first stage carried, its sum is 0. So the second stage has nothing to carry. The two carriers are mutually exclusive, always. There is no collision for OR to lose. Let that settle for a second. It's 3 steps, and it's worth rehearsing out loud. 2 anchors here, and they're the ones worth saying twice. First, if the first half carried, its sum is 0, and a 0 can't carry again. Second, 2 halves and an OR make a whole. When an exam asks why OR is sufficient, your brain should instantly jump to mutual exclusivity first carry fires. Therefore, partial sum is 0. Therefore, second carry is 0. And know the 2 trick variants, because professors love them. Variant 1. Replace the OR with XOR. The carries are never both 1, so OR and XOR behave identically. The circuit still works perfectly. The trap is confidently answering, it breaks. Variant 2. Replace the OR with AND. The 2 carriers are never both 1, so an AND of them is permanently 0. The carry-out dies, and every carry-producing case fails. The common drying mistakes, while we're here, omitting the OR gate entirely, and wiring the carry-in into the first half adder instead of the second. Curiously, that second mistake still produces a correct adder, remember? The 3 inputs are symmetric, but draw the standard form, A and B into the first half adder, carry in into the second. Let's verify the build on the 2 carry cases by year. Case 1. All 3 inputs 1. The first half adder sees 1 and 1. Partial sum, 0. First carry fires. The second half adder adds that 0 to the incoming 1. Sum 1, second carry, 0. The OR sees 1 signal high. Carry out 1. Sum 1. Carry 1 exactly what counting predicts for 3 ones. Case 2. A, 0, B, 1, carry in 1. The first half adder, partial sum 1, no carry. The second, 1 plus 1, sum 0. Second carry fires. Carry out 1. Again, correct? Both carry paths exercised, both deliver. And notice the second carry is not optional. Remove it, and that second case silently fails. Quick inventory, because exams count gates. A half adder, 1 XOR, 1 AND. This full adder, 2 XORs, 2 ANDs, 1 OR. 5 gates total. So the entire build boils down to this. Half adder on A and B, half adder on the partial sum and carry in. Carries merged by a single OR legal because the 2 carries can never fire together. So one column is completely solved. Now let's zoom out and find out why this small circuit matters so much. The full adder is 1 column, and n columns make an n-bit adder. Chain 4 full adders, each carry out feeding the next stage's carry in. The very first bit has no incoming carry, so use a half adder there or a full adder with its carry in tied to 0. And notice, a full adder with carry in 0 is itself a half adder. Its equations collapse to A XOR B and A and B. That's another standard exam question, already answered. Now run our opening example through the hardware. 1011 plus 0110. The carries ripple leftward, stage by stage, exactly as they did in your hand calculation. Same columns, same carries, same answer, 10001. This circuit is your paper method, frozen into silicon. The anchor, carries ripple right to left, exactly like on paper. One sentence about the future. Each stage's carry must cross 3 gate levels, an XOR, then an AND, then an OR. So an n-bit ripple adder slows down in proportion to n. That problem is called carry propagation. Its solution, the carry look-ahead adder, is the next lesson. And further ahead, multipliers are built from stacks of these same full adders. But takeaway, an n-bit adder is n-chained full adders, and bit 0 degenerates to a half adder. Before you go, don't rewind, retrieve. 3 questions. Give yourself 3 seconds each. Question 1. The half adder equations. Sum equals A XOR B. Carry equals A and B. Sum is XOR. Carry is AND. Question 2. A full adder receives 1, 1, 1. What are sum and carryouts? Count the ones. 3. In binary, 1, 1. Carryout 1, sum 1. Odd parity, majority votes. Question 3. In the 2/2 adder build, replace the OR with XOR. Broken or fine? Fine. The two carries are never both 1. So OR and XOR behave identically there. 3 for 3? Then you own this topic. 2 homework problems will make it permanent. First, build the full adder from 9 NAND gates. Second, build it from 3 half adders and explain why the third one's carry output is permanently 0. And the final recap. The sentence is worth carrying into the exam hall. Sum is XOR. Carry is AND. XOR is addition without the carry. 1 plus 1 is 1, 0. The half adder, half the job. No door for the carry. The full adder, XOR everything. And any 2 ones make the carry. Count the ones, write it in binary, and 2 halves and an OR make a whole because a stage that carried sums to 0.